Excellent. Thank you so much. Hello, everyone. Welcome to our live session for today, Thursday, July the 2nd. My name is Matthew. I am one of the instructors and course developers for the astronomy classes and astrobiology class that we run. And Alexander is doing a lot of our development and tech support. I'm going to pass this over to Professor Impey, and Chris will get started on questions right away.
Okay, yes, the floor is open for questions on astronomy.
All right, the first question that we have is from Varsha, who sent an email. Varsha is it looks like a bachelor's geology student from India, and they would like to know, how can they become an astrobiologist?
Well, the path to astrobiology is a little indirect these days. It is a substantial niche of astronomy now. It's a growing niche. But the background of astrobiologists varies enormously. Some really come from a pure astronomy background where they've added on some biology. Some do come from a life science background, and some, like you, would come from earth science background. And earth science into astrobiology is quite a reasonable fit, actually. So one of the ways to get there is actually through planetary science department. Some of the big ones or most famous ones are at Cornell and Caltech, and there are a few other places that have very big planetary science departments, like Arizona, of course. So it's fairly easy if you're in a planetary science department to use all your geoscience background, because planets are just rocks after all. And most planetary science departments are now doing astrobiology research because they're worried about habitability of planets, and they're involved in space missions or telescopic observations of exoplanets. So I think that the easiest path for a geoscience person into astrobiology may be through planetary science program, graduate program, say. It can also work in an astronomy program, and so we do have students that have come into our PhD program who had a geoscience background. Sometimes they had to make up a little physics, undergraduate physics, that they may have missed, because most astronomy PhDs were physics bachelors. But with that deficiency aside, I think that's a reasonable path into the field.
Excellent. Thank you very much. The next question is from Ravi, who has a question about hot Jupiters. Do hot Jupiter atmospheres consist of hydrogen, helium, and other light gases like our Jupiter and Saturn? And if so, how do they retain these constituents when they're so close to a star? Wouldn't those light atoms and molecules be blown off given the mass and gravity of the planet?
So yes, hot Jupiters are similar in composition to the normal Jupiter in our solar system, which is to say overwhelmingly hydrogen and helium, the two lightest gases, the two most abundant gases in the solar nebula. And so they formed in that same way. They probably have small rocky cores, as the giant planets in our solar system do. To the second question, indeed, if they are on very close orbits, if they're hot Jupiters on orbits that may be days or even a few weeks, then you can work out what the temperature is at their atmosphere, and it could be 1500, 1700 centigrade. And at that level, yes, the atmosphere is going to slowly ablate. So having parked in tidally locked orbits very close to their parent star, their atmospheres are slowly being ablated off into interstellar space and will not last forever. The rate is still quite slow because they're not that close to the star that it's happening at an incredible rate. But in some hundreds of millions of years, they could lose a substantial fraction of their atmosphere. So in old systems, the super Jupiters, the hot Jupiters, may not be there anymore because viscous forces may have, the ablation may have taken away the outer atmosphere, and then viscous tidal forces may have pulled the rocky core into the star, and so there's no more hot Jupiter.
Excellent, thank you. The next question is from one of our live participants. Junaid would like to know, if Hawking radiation is a true concept for black holes, then where does the mass of the black hole go?
The mass of the black hole essentially goes into radiation. So E equals mc squared, that's a famous principle Einstein developed over 100 years ago. And so mass, any mass has an energy equivalent. And in this case, you're essentially taking some of the mass of a black hole and turning it into thermal radiation. Now that thermal radiation has an effective temperature of very small number, a tiny fraction of a degree. For a solar mass black hole, it would be about a billionth or a few billionths of a degree Kelvin. But that is essentially the radiation that is, and you could use E equals mc squared to work out, given the temperature and the surface area of the black hole, how much it was radiating, just like any hot body, how much mass it was losing. And it turns out to be a very tiny amount, which is why the evaporation timescale of a star like the sun turned into a black hole is about 10 to the power 57 years. Incredible long time.
Thank you. The next question is from Ayush, who would like to know, do the special and general theories of relativity have significant roles in sending landers to planets in our own, they say galaxy, but let's say, sending spacecraft to various places in the solar system or the galaxy?
Right. Relativity does come into play in places you might not expect. Now, special relativity is typically only applicable in situations of speeds close to the speed of light. So special relativity really doesn't feature in planetary science missions because all these spacecraft, however fast they're moving, are at very tiny fractions of the speed of light. Now, in particularly careful plotting of trajectories, it may be that you need to include the relativistic correction, but most spacecraft telemetry and spacecraft orientation and projection of their orbits is not precise enough for that to be significant. For general relativity, there's also no substantial effect in the solar system because there's no gravitational system, a situation where the gravity is intense enough for general relativistic effects to come into play. If there were, it could come into play in timekeeping and time dilation. So the simple answer is no, relativity really doesn't play into solar system physics or exploration at all.
Excellent. Thank you very much. The next question is from Swarnim, who would like to know what will happen if a gamma ray burst hits a black hole? So what happens when these things interact?
So if a gamma ray burst is a fantastic detonation, like a hypernova almost, the most powerful explosion known, which radiates enormous amount of energy and particles, and the energy is coming out at a very high effective temperature, which means gamma rays. And it's coming out in a beam because the spinning collapsed object that's left behind for a gamma ray burster is likely to be a black hole with a spin axis. So should a black hole be in the path of a gamma ray burst, what would happen to it? And the answer is not very much, because the black hole is a tomb of matter. It's a piece of space-time that's pinched off. And what would really have an effect is that the gamma ray burst would hit the accretion disk or the accretion zone around the black hole, and there it would cause a lot of havoc. It would probably disrupt the accretion disk. It may destroy the accretion disk, and so the black hole would lose its source of fuel that it had from the accretion disk. The black hole itself is just not going to be affected by the sheer blast of radiation. That radiation, of course, in the path of the black hole will disappear, will be trapped by the black hole, adding very slightly by E equals mc squared to its mass. But otherwise, the black hole is unaffected.
Excellent. Thank you very much. The next question is from one of our live viewers who would like to know if electrical discharge is possible in space. So can you build up electric charges? Can do you have to worry about electric, discharges and shocks in space?
Mm-hmm. Generally, no, because an electrical discharge, if you think about it, if you think about lightning, for example, as an extreme form of discharge, it's caused by having charge be able to flow by creating an ionized path, essentially disassociating neutral, stable atoms into their positive and negatively charged components. And since an electric current is just a flow of current of either net electric positive or electric negative charges, that's what a discharge would be. Now in space with a vacuum, there's obviously no medium to be ionized. So in general, you don't have any issue like that. What can happen, though, is an actual flow of the charged particles themselves, almost like a beam, and then in that sense, charge can be carried. So if sufficient static charge were built up in an electrical situation, it's possible that it could send, because it builds up a strong positive or a strong negative charge, it's possible it could send an actual beam of electrons or ions to neutralize with another object. This is the danger, for example, when astronauts were servicing the Hubble Space Telescope, working with electrical panels and the electrical power units for the Hubble Space Telescope instruments. They grounded themselves as part of their work, and there was a significant chance of that kind of a beam discharge happening, which would have been catastrophic. It wouldn't have been fatal to the astronauts, but it would have been catastrophic to the delicate instruments of the Hubble Space Telescope.
All right, the next question is from William, who is on with us live. What are your thoughts on the origin of the moon? I've heard different things, one large Mars-sized object or many smaller impacts.
It's been a standard theory now for several decades that the moon was formed by the impact of a Mars-type object, a protoplanetesimal, early in the history of the solar system with the infant Earth. And it probably happened within a few tens of millions of years after the formation of the solar system, 4.54 billion years ago. This story makes sense in terms of the fact that the moon is mostly mantle material, has no iron or metallic core, and therefore no magnetic field. And because of the moon rocks were brought back by Apollo, we can show that the moon is essentially made of Earth mantle type material, not crust and not core, but mantle. And that's the material that would have been spun off into space to coalesce into the moon. Also, simulations have shown that an impact could lead to the ejection of a moon mass object that would then eventually circularize its orbit, as the moon has done around the Earth. This picture has had some flies in the ointment over the years. There was a time when people working on the Apollo moon rocks just thought the detailed geochemistry of the rocks was not as neatly consistent with Earth mantle material as they thought. Very recently, just this week, there's been a news story that the metal content of the moon rocks that we've sampled is also slightly inconsistent with it being Earth mantle material. So every few years, I would say there's a challenge to the theory. There's no alternative theory, and the idea that the moon was, that it's a series of small impacts actually doesn't work. The only way you can generate a large object is by a truly massive collision. So that's still the best theory. But of course, it happened so long ago, just after the formation of the solar system. There were no witnesses and there's no direct evidence. So this may be always hard to be completely sure.
All right, the next question is from Time Lord, who's on with us live. How can we get insane amounts of energy? I'm talking about enough energy to get us humans to be able to make something like a Dyson Sphere.
Well, the way we can get a lot of energy, of course, is to use more efficiently the energy source that's always available to us, which is the sun. So the Earth, at its distance from the sun, intercepts about 1/billionth of the total power of the sun. And through our relatively inefficient methods of capturing the sun's energy, since we don't use solar power on a large scale, we utilize about 1 part in 1,000 or less of the sun's energy. So we're using about 1/trillionth of the sun's total energy. A Dyson sphere, in its concept, would use a significant fraction of the sun's energy, maybe not 100%, but maybe 10% or 1%. So it's literally billions or tens of billions of times more efficient than we are right now. So there is plenty of energy available if we could construct something like a Dyson sphere. Obviously, there are intermediate steps to do that, because constructing something around the sun at that distance with a physical plant would be extremely expensive and difficult. So an intermediate step would be for us to have a capability in high Earth orbit or at a Lagrange point to capture with huge solar collectors a more substantial fraction of the sun's energy and then convert it probably to beamed pulsed energy down to the Earth's surface and then capture it and store it. That would be a way of increasing our energy supply for the Earth and for doing things that are exciting technology-driven projects by maybe 10 or 100 times over what we can do present day.
The next question is from Astrophysics, who's on with us live. And they would like, they're trying to understand how to visualize or understand a black hole. So the question is a black hole a dark spherical object, or is it just a dark hole? In illustrations, they appear to be like rabbit holes, but this is confusing because what's underneath the black hole's space-time fabric and not inside it? I think the problem is this 2D versus 3D representation.
Yeah, it's a good question, because it's a perennial problem in astronomy, not just with black holes, but with other objects, orbits, and curved space-time, and so on. How do we visualize something that's occurring in 3 dimensions, X, Y, and Z? How do we visualize that or represent that? And the answer is we have to represent it on a surface, on a page or a computer screen, and that's 2-dimensional surface. So we're endlessly trying to find analogies that map 3 dimensions into 2. And so the standard rabbit hole version of a black hole, if you like, or sort of a distorted sheet that's pulled down in some area, it's an inadequate representation. It's not accurate. And so that's, I think, the most important thing to remember, that any 2-dimensional mapping or representation of a 3-dimensional situation is fundamentally inaccurate. And so what's the best way to think about it? Well, in general, in 3 dimensions, black holes are spherical. So thinking of them as spheres is correct. However, they're not spheres embedded in a space, because they represent the rupture of that space-time, just essentially like a pinprick hole where the space-time actually disappears in all 3 dimensions into something that cannot be accessed by our observation. I think this is just a fundamental problem. You have to go with the 2-dimensional analogy up to some degree, and then just recognize that it's not really the true situation. The mathematics in the end is what really describes the black hole.
The next question is from Red Unleasher, and I can't remember if we had this question last time. It sounds familiar, and maybe it's just a repeat that somebody asked that we didn't get to last time. But what is cyclotron and synchrotron? And we hear that a lot in reference to astronomical objects, but also here on Earth.
Right. So cyclotron and synchrotron radiation are sort of fundamental physics concepts. They involve the movement of charged particles in magnetic fields. So if just take an electron moving in a magnetic field, if you have an electron moving in a magnetic field and that electron is not traveling at a high speed compared to the speed of light, so we would say sub-relativistic, then it emits what's called cyclotron radiation, which is a beamed, accelerating a charged particle causes it to radiate electromagnetic waves. That's a fundamental precept of electromagnetic theory. And in cyclotron radiation, that radiation comes out with a particular energy corresponding to the period of the energy of the electron moving in the magnetic field. A physical example of cyclotron radiation occurs in a pulsar, where the pulsar has magnetic field lines, and free electrons traveling in those magnetic field lines emit cyclotron radiation. Because of the magnetic field lines, that radiation is actually polarized, and that's one of the hallmarks of cyclotron radiation. The first cyclotron as a physical particle accelerator was developed in the 1920s, I think, and it's been a part of particle physics for quite some time. Synchrotron radiation is just an extension of that idea to the situation where the charged particles are moving relativistically or close to the speed of light. It's the same idea, though. They're spiraling in magnetic fields. When the electrons are traveling at close to the speed of light, the radiation that would normally come out in essentially a fan is forward focused by Doppler boosting, and so is essentially coming out along the direction of travel of the electron, is beamed, as we would say in physics terms. And so synchrotron radiation is a hallmark of extreme astrophysics, say, that occurs near a black hole, where the magnetic field lines of the black hole and the gravitational potential energy are enough to create enormous acceleration of electrons to relativistic speeds, and the radiation that comes out is synchrotron radiation. And that's seen with radio galaxies, with quasars. It's also polarized, representing the order of the magnetic field where the radiation emerges. And so it's a fundamental tool of astrophysics, and it, of course, is also created by accelerators on the Earth, where it's often used in biomedical imaging and other applications.
The next question is from an email. Ezekiel emailed and would like to know if you can explain the process of random particle creation related to what we've talked about, matter and antimatter pairs that are spontaneously created in the vacuum of space.
Mm-hmm. Right. So there is a phenomenon in physics that's been known for a long time, over 50 years, and been demonstrated in the lab. So it's a real effect, not just a theory, where essentially from the vacuum of space, so it doesn't have to be any physical medium, particle-antiparticle pairs will spontaneously appear and then disappear. And the boundary on this is really given by Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle in physics has two forms. It has one that involves the product of uncertainty and momentum and velocity of a particle, which is equal to or less than the Planck constant. And the other form is the uncertainty in the energy or time of an energy transition, which is equal to or less than the Planck constant. So what the energy form of the Heisenberg uncertainty principle says that you can borrow a certain amount of energy for a short enough time, such that the product of that amount of energy that you borrow, delta E, times the amount of time that energy is available, delta T, is given by the Planck constant. And so for shorter and shorter times, more and more energy can be borrowed. And what that energy can do, of course, is create particle-antiparticle pairs. But to satisfy the Heisenberg principle, those particle-antiparticle pairs have to come in and go out of existence very quickly. And the more energy that's borrowed, and so the more massive particle-antiparticle pairs created, the less time then they can exist. And in any event, for whether it's electrons and positrons or protons and antiprotons, these times are tiny fractions of a second.
Excellent. Thank you very much. The next question is from one of our, is also from an email. So as these matter and antiparticles annihilate each other, they release pure energy. Is there any evidence that this could account for a portion of the expansion of space-time or be somehow related to dark energy?
That's a thought that a number of physicists and cosmologists have had, that if dark energy is causing the expansion of space-time, then and the source of it is the energy of the vacuum, maybe it's the vacuum energy that's driving the cosmic acceleration. And in general terms, this idea works. So it is a plausible mechanism for the accelerating expansion of space-time, that this energy, this net energy that causes an expansion, which essentially acts like a negative pressure in physics terms, could come from the vacuum of space itself. We know that the accelerating expansion does not seem to depend on time or location in space. It's been the same over cosmic time, and it doesn't matter where you are in the universe. As the universe expands, that amount of vacuum energy stays constant. So it's a drawing on a reservoir that continues to increase as space-time expands. So yes, it is plausible to think of it in terms of borrowed vacuum energy. The trouble is we don't know the physics of this mechanism. We don't have a true physical mechanism for why space-time would be accelerating in its expansion like this.
The next question is from George Papadopoulos, who would like to know, does the gravity of every object in the universe, planets, stars, galaxies, etc., regardless of different distance, have an effect on our planet? And is it true that everything is connected in this way?
In principle, yes, because the gravity force is an inverse square law force in the Newtonian version, and Einstein approximates the Newtonian version when gravity is weak. And 1 over the square of a large number becomes very small, but never becomes zero. So gravity has an infinite reach. And so in principle, yes, all objects have a weak, significant, non-zero effect on all other objects. This was really clear to people at the beginning of gravity theorizing. It was aware to Newton, of course, because he was the first to come up with an inverse square law of gravity, and he considered it a reason why the universe had to be infinite, because if the universe were not infinite, and gravity had an infinite range, then you'd have to have a universe that was essentially collapsing. So this same idea led Newton to the idea of an infinite universe. Now, in the modern era of general relativity, this was realized by Ernst Mach, a physicist who was a contemporary of Planck and Einstein, and it became Mach's principle. And Mach's principle was indeed that all objects are affected intrinsically by all other objects due to the force of gravity. This has become almost a philosophical statement in physics as opposed to a practical statement, because in practical speaking terms, most objects are only influenced by the nearest objects to them. So I move around on the Earth, and the Earth controls what happens to me. I am affected, of course, in principle, by distant quasars or distant galaxies, but it doesn't operationally affect how I behave on the Earth. So this is one of these things that becomes almost an issue of philosophy rather than practical physics.
Thank you. The next question is from Chris Ripple, who sent an email asking, where would astronomers expect not to find planets around stars?
That's a good question. One of the places they would not expect to find planets is around stars that had died violently, because the most violent detonations of stars, the supernovae that lead to black holes, those stellar explosions are very likely to disrupt the orbits of planets and send them skittling off into space, or disrupt their orbits largely enough so that they're not bound to the system. So it would be a surprise to see planets around black holes or neutron stars. And of course, that's why the very first planets to be detected, first exoplanets to be detected, people forget this, it was not 51 Peg, which the award of the Nobel Prize was for, to Michel Mayor and Didier Queloz. The first pulsar planets were detected in 1992, 3 years before 51 Peg. And that was why it was such a surprise, because that system, a pulsar with small planets, including a sub-Earth-sized planet, I think there are 3 planets confirmed now, that's just not a place you'd expect to find planets. And speculation was, were they captured afterwards? Because how could they possibly survive the explosion? So short answer, neutron stars and black holes are places where we do not expect to find planets, and possibly the very lowest mass stars, where there might not be sufficient material left over from their formation to create planets of any mass.
All right, the next question is from Yana, who sent an email. What is the relationship between space weather and Earth's terrestrial weather?
It's quite strong, because the Earth is a closed system in a sense. We have an atmosphere, and most of the Earth's weather happens in the meso realm of the atmosphere, which is this realm up to 10 kilometers high, basically. And then the atmosphere thins out into space. So in large part, the Earth's atmosphere is self-contained, driven by the overall solar energy. But space weather, so the fluctuating conditions in space caused by energetic particles and solar flares and cosmic rays, for example, they affect the Earth's weather significantly just because they have high energy. So high energy particles, like cosmic rays, carry enormous energy, each one. High energy radiation, also like cosmic rays or like the sun's UV radiation. And the sun fluctuates a lot more in ultraviolet light than it does in visible light. Are likely to drive larger changes in terrestrial weather because of the energy deposition into the upper atmosphere that works its way down through the atmosphere and can drive Earth's changing weather. And so space weather has a lot of leverage over the Earth's weather because these small components of the energy of a star or its variation can actually disproportionately cause fluctuations in what we witness from day to day or week to week.
The next question is from one of our live viewers. Yoga would like to know, what happens when gravitational waves meet each other? Do they add up or cancel out? They
have different modes, actually. So gravity waves are tensor waves, to use the mathematics, which means they have both transverse modes, like waves in water or a wave on a string, for example. If you make a string move up and down, they have compression waves like sound waves where things move backwards and forward longitudinally. So they're transverse, they're longitudinal, they work in all three dimensions. And yes, they are additive. So, but you have to use the tensor math of adding in three dimensions with vectors. So yes, in principle, gravitational waves can pass through each other. They will add and subtract. And you can, if you work out the three-dimensional components of those waves, you can say at any given place what the sum of two gravity waves passing through that location would do.
Excellent. The next question is a very general one from a live viewer who would like to know, what is the Big Bang? Can you explain what it is and why it is important?
Sure. The Big Bang is astronomers' idea of how the universe came into being. The time to the Big Bang is well measured by observation to be 13.8 billion years. And the Big Bang is essentially a situation of extremely high temperature, energy, and density from which our present large, old, and cold universe emerged. We don't know what caused the Big Bang. The theory does not describe that. And we really can't account for the physical conditions at the Big Bang itself, because when we extrapolate backwards, we infer a situation of infinite density and infinite temperature, which we have no physical theory to describe. However, as the explosion, which is not really explosion because it's not occurring into an external dimension, so the phrase Big Bang and the idea of an explosion are misnomers. They're erroneous. They lead us astray in our thinking about it because it created all space and time from one iota of space-time. Our theory, the Big Bang theory, ably describes the conditions in the universe as it emerges from this hot, dense state. And so the three fundamental pieces of evidence that lead us to believe that's a correct theory of the history of the universe are the fact that we see microwaves left over from the creation, and those microwaves have exactly the right temperature that we expect them to have after the universe is expanded by a large factor of thousands over those 13 billion years. We see the galaxies all moving apart from each other, the cosmic expansion measured by Hubble, and if you run that clock backwards, you infer something like the Big Bang. And crucially, we also can explain where the helium in the universe came from. The universe is about a quarter by mass of helium, and if you work out the history of all the stars and all the galaxies, who are making helium for the most part, there's not enough helium made by all the stars and all the galaxies to account for a universe that has that much helium. Yet the universe itself was once as hot as the center of a star and made helium in the first few minutes after the Big Bang. And the theory beautifully predicts the amount of helium and other light elements like deuterium and lithium that we see in the space between stars and galaxies. So these three pieces of evidence have convinced most astronomers that the Big Bang is an excellent theory.
All right, the next question is from Vilpul Kumar, who would like to know, what is the reason for the movements of planets in elliptical orbits?
It's elliptical orbits are just a constant energy condition. So in a sense, circles are special cases of ellipses. So the general case of two objects held together by gravity is always going to be an elliptical orbit. So it's essentially the natural condition. And if you work out the energy of any object in an elliptical orbit, it will have some combination of kinetic energy due to its speed of motion in the orbit and potential energy caused by its gravitational potential to the object it's orbiting. And those two trade off against each other such that the sum of them, the total energy in the orbit, is constant. For example, that's how Kepler's laws come about. So when the object is closer to the star, for example, if it's a comet or the Earth itself, it moves faster. So it has less gravitational potential energy and more kinetic energy. When it's farther from the star, it'll have slower speed and therefore lower kinetic energy and higher gravitational potential energy. So in a sense, of a sort of constant energy situation of two objects held together by gravity, an ellipse is the natural case.
Thank you. The next question is from Tene Kona, who's on with us live, who would like to know, What type of distortion or energy dissipation does light face when it travels really insane long distances?
Um, the what happens to light when it travels long distances is an interesting question. Some people, there were a set of theories that have been fallen out of favor and mostly disproven called tired light theories. The idea that the light, I mean, not metaphorically got tired or exhausted, but that the light lost energy just by traveling through space for a particularly long time. Obviously, there's a simple optics principle at play that a beam of light or a focused, concentrated area of light, unless it's perfectly concentrated, will spread out and disperse and diffuse and lose energy as it moves through space. But apart from that, what happens to the wave itself is that in principle nothing happens to it in a pure vacuum. It continues to travel at the same speed, 300,000 kilometers per second, and has the same properties. However, light traveling through space on large scales is traveling through an expanding space-time situation, the expanding universe. And that expanded space-time with an oscillation in it of electromagnetic waves means the energy of that oscillation reduces over time, and that's called the redshift. And that's cosmological redshift, which is distinct from a Doppler shift. And so the main effect of light traveling through space is that since it's traveling through expanding space-time, the effect of that is to stretch the wavelength of light. And a longer wavelength means lower energy and a redder color. So that's the redshift.
Excellent. Thank you very much. The next question is from I Am Nitin, who would like to know, is there any alternative for rockets to get into space? And I'm assuming they mean to the current multi-stage chemical rockets.
What was the first word? Is there any alternative?
Yes, I'm sorry. Are there any alternatives for rockets to get into space?
Well, the main method of rocketry, even in the era of SpaceX and Blue Origins, is chemical rockets. So rocket technology has improved, and we're witnessing dramatic gains in the efficiency of rockets that take things into orbit now, including astronauts from SpaceX just a few weeks ago. But really, fundamentally, rocketry has not changed since Goddard in the 1920s or since the Saturn V rocket took astronauts to the moon in the 1960s. It's still fundamentally the same thing. It's very efficient and volatile chemical energy fuels converted into high-velocity exhaust gases, and the conservation of energy and momentum means that the rocket travels up into space, into orbit. So everything has really been the same through the whole history of the space age. Alternatives to that would involve completely different mechanisms of energy, and obviously the next efficient one looking to the future would be fusion or fission energy. These are mechanisms that we can harness fission on the Earth. Obviously, nuclear power reactors use that. But fusion we have never harnessed in a sustained way, in a controlled way outside of a bomb. Those would be the ways of increasing the efficiency of rockets by very many orders of magnitude, maybe 5 or 6 orders of magnitude. And that would be a game changer, of course, for space travel. But that looks like that's decades away.
Excellent. The next question is from Fernando, who's on with us live. If money and politics were not a problem, where would be the best place to have a telescope and why? Somewhere close to Mount Everest?
It's an interesting question of where is the very best place to have a telescope on the Earth. It turns out that it's not always better to be higher. Witness the fact that, a large, uncomfortably large fraction of the climbers who've been on Everest have died. It's an extremely inhospitable place. And actually, there's a lot of extreme weather up there. Many of the climbers who died on Everest or the other world's highest mountains have died in storms or, in their conditions of extreme cold and wind. And so the world's highest mountains actually tend not to be really good places for telescopes. A good example of this is down in Chile. So Chile is home to the world's largest collections of telescopes, and I've used a number of them. And they're both in the middle part of Chile and up in the north in the Atacama Desert. But these telescopes and the Andes, a very high mountain range, runs right through Chile, and Aconcagua, the highest mountain in South America, I think 3,000 feet high, I'm not sure exactly how high, is not that far from some of the major observatories. But the observatories are built at high elevations, but not the highest elevations, because again, the conditions are just too extreme in the highest mountains. So the Atacama Desert observatories are up at about 18,000 feet, but there are much higher peaks nearby. The mid-latitude Chilean observatories like Las Campanas and the European Southern Observatory and Cerro Tololo are at altitudes of 7 or 8 or 9,000 feet, when again the high Andes go twice that high. So that means typically you're looking for places that are high but not too high. They're not at the peak of a mountain range where the weather and conditions are too extreme, and they have very stable weather. In a sense, the Chilean observatory is in the lee of the weather that comes over from Argentina over the Andes, and it tends to shelter them from that, and they have an inversion layer, so it's very stable conditions. Hawaii is the other major observatory site for good reasons, because the trade winds are reliable, the weather is often dry, and Mauna Kea is again high mountain but not super high. So you do want high altitude, but not too high. You need to be in a place that has extremely stable weather patterns, and hopefully an inversion layer which will trap most of the water moisture, which can cause problems for infrared observing and can cause, through its turbulence when there's a lot of cloud activity, bad seeing or bad image quality.
Excellent. The next question is from Amaya, who would like to know, how often do hypernovae happen?
They are extremely rare because they represent the death of the most massive stars and the most extreme stellar detonations. And the number of massive stars is far lower than the mass than stars' mass of the sun, which itself is much lower than the mass of stars like red dwarfs. So the fraction of all stars that die as hypernovae is very small. I think it's less than 1 in 1,000, maybe 1 in 10,000, because it's the most extreme high mass stars that, of course, have correspondingly short lifetimes of fusion and very quickly accelerate in a crescendo of nuclear activity to the final state of their collapse and detonation. So very rare objects, luckily, because they're also quite dangerous if they were close to us. So the fact that they're rare means the distance to the nearest hypernovae is very likely to be hundreds or thousands of light years.
All right, the next question is from Malik, who would like to know if it's possible to produce oxygen on Mars by taking microorganisms from Earth to Mars.
Not yet. Mars is not really habitable on the surface. So Mars's surface has very little atmosphere, 1% of the atmospheric pressure of the Earth, and only carbon dioxide composition. It's also extremely cold. So Mars's surface is irradiated with cosmic rays and high-energy particles. It's arid, it's dry, and that's inhospitable for microbes. It's possible that microbes could survive under the Martian surface, and we could maybe find places where microbes could subsist metabolically on materials that are available in the rock, and they could then generate oxygen. They could be oxygen-emitting microbes, and that oxygen would percolate up to the surface and contribute to the atmosphere. But the effort required to do that on a large scale is truly prodigious. A better way actually to get oxygen out of the Martian situation is actually to just use the rocks themselves, because most of the rocks are, of course, a lot of carbonate material in the rocks, which is binding oxygen to carbon, and there are electrical and electrochemical mechanisms for dissociating that oxygen and releasing it. And in fact, in Mars colony plans or Mars habitation plans, there are methods that we already know how to use to liberate oxygen from Martian rocks so humans could breathe it and it could be part of their habitat there. But again, that's only on a small scale. That's not any way we could really transform the planet or terraform it.
Thank you. The next question is from one of our live viewers who would like to know, why is it that planets are round but galaxies are flat?
It's a good question. Well, planets are mostly round. I mean, the definition of a planet includes the fact that it has sufficient gravity, self-gravity, to equalize its size in all directions. It's the most symmetric object where the gravity force operates equally in all directions. So Planets are round because gravity is operating symmetrically and pulling the surface and the material equally in all directions, and that will tend to a minimum energy configuration, which is a sphere. Galaxies are not in the same situation because galaxies are not solid objects. Galaxies are essentially mostly empty objects because they're made of billions of stars, but the spaces between the stars in a galaxy is millions of times bigger than the size of the stars themselves. So the galaxy is overwhelmingly empty space. And so the reason galaxies have shapes at all is also because of gravity, but it's not the gravity of a solid material or a solid object. It's a gravity of a large number of stars operating mutually by the gravity they exert on each other. And the shapes of galaxies, in particular, the difference between spirals and ellipticals, is actually imprinted by the initial conditions of the gas cloud that formed those stars in the first place billions of years ago.
Excellent. Thank you very much. The next question is from an email, and Tanvi would like to know, what is the difference between astronomy, astrophysics, and cosmology?
Astronomy is colloquially used to refer to looking at the night sky or the objects of the night sky, describing the phenomena of the night sky, the objects that you can see there, stars and planets and a few galaxies. And it's sort of a descriptive term for what you might see out there. Astrophysics, it goes a little beyond that and implies that there's physics that helps us understand the objects in space. And if you study astrophysics, you're actually studying the physical mechanisms that go behind stars and galaxies and planets. In other words, how did the planets form? What are stars made of? Where do they get their energy from? And asking a series of physics type questions. That's astrophysics. Cosmology is different again because cosmology does not relate so much to the individual objects themselves, planets, stars, and galaxies, but addresses the universe as a whole. So cosmology is the subject of the universe as a single entity, its history, its origin, its size, its shape, and its future.
All right, the next question is from an email, and they ask, what if our planet Earth replaced the planet Mars in its orbit? So what if Earth formed where Mars is at the beginning of our solar system?
That's certainly a hypothetical that could happen in a different solar system. I mean, we could imagine them having formed and swapped places. They're not that different in mass and size that's not a plausible scenario. So all the terrestrial objects you can play these games with. If the Earth had formed where Mars was, of course, it would not be habitable now because Mars is just outside the habitable zone. So the Earth would have been subject to the same problem that Mars had. Mars has an extra problem because it's small and far from the sun, its temperature is cold, and it's not been able to retain its atmosphere. The Earth would have been massive enough to retain its atmosphere if it was at Mars distance from the sun, but it would have still been cold and probably too cold to be inhabited. In other words, the oceans would likely have frozen all the way down to the bottom, and that most biologists think would have been a condition where it would have been hard for life to get started. Maybe not impossible, because there was still geological activity, but it would have made life on Earth a different proposition and a much less favorable one.
All right, the next question is from one of our live viewers, and Vibhav would like to know, or read something about the University of Ohio mentioned that a black hole may or may not undergo a supernova explosion when it forms. Is that true? And if so, how is that possible?
The conventional story of black holes is that they are always preceded by a supernova because you actually need a massive star to get to the end of its life and undergo a core collapse. And that core collapse is what compresses the central region to the situation of a black hole. I think there's theoretical speculation and some simulations that indicate you could have a sort of failed supernova explosion. It might occur because of the spin of the black hole and the core collapse occurs in an asymmetric way, so it doesn't actually lead to the classic core bounce, which is what generates a blast wave that corresponds to the supernova. So it's possible that some extreme conditions of rotation, or perhaps the uneven environment of the vicinity of the object when it collapses, might lead the supernova explosion to be suppressed or distorted or damped down compared to a normal supernova. But I don't actually know of a theory where there's no explosion at all, because the explosion goes with the core collapse that leads to the black hole.
Excellent. The next question is from one of our live viewers. Can you please explain Cherenkov radiation?
Yes, Cherenkov radiation is radiation that occurs when a particle is actually moving through a medium. Could be a liquid medium, could be a gas, could be ionized medium. And this particle is relativistic. It actually leads to a relativistic forward-directed light cone of radiation that can be used to signature that particle's arrival in the detector. And that Cherenkov radiation also is subject to relativistic effects because the particle is traveling essentially at the speed of light. So it's very forward focused. It can be detected by photometers or photomultipliers. And so it's a standard technique of particle physics to detect Cherenkov radiation caused by the arrival of a relativistic particle.
Excellent. Thank you very much. The next question is from one of our live viewers. What would happen if Einstein is proved wrong in the future?
It wouldn't be an entire surprise if physics changes. Newton wasn't proven wrong necessarily. His theory still works in weak gravity regimes, but Einstein's theory is proven to be a better, more accurate theory. We know it's not the final theory because it does not suitably account for all the properties of black holes, even though the theory is used to predict their existence. And we also know that the theory cannot be reconciled with the quantum theory that applies on microscopic scales. So it not only would not be a surprise, but it's anticipated that there will be a subsequent theory of gravity and maybe a theory of everything that supersedes Einstein's theory. Now that will not probably make it formally wrong. That'll just mean it's been superseded by a theory that includes Einstein's theory as a special case in a particular set of circumstances. And that's typically what happens in the evolution of physical theories, that the previous theories are not completely overturned or shown to be absolutely wrong, but they're shown to be a different, you're moving to a different paradigm, if you like. You're moving from the paradigm of linear space and time that are independent of each other to the coupled space-time of Einstein. So it's a different way of looking at the situation, a different realm of applicability, and a different physical basis.
Excellent, thank you. The next question is from AV, who's on with us live. With the current level of pollution and global warming, how long can life last on the Earth?
Well, that's the big question, isn't it? We hope a long time. The climate change that we're being subject to, which is likely to heat the planet by another 2 degrees centigrade in the next 10 or 15 years, which is considered a very dangerous thing. It will lead to very bad consequences for human health and for the world economy, is not going to cause the Earth to be uninhabitable. So none of the climate change we're looking at in the foreseeable future is actually going to render the Earth uninhabitable. That would take a much more dramatic episode, like a true global catastrophe of nuclear war or biological warfare that rendered the planet toxic or killed all people. So really apocalyptic scenario. So climate change on its own is unlikely to make us uninhabitable. And if you look at the long history of the Earth, of course, through the ice ages of the last 100,000 years, the Earth has had temperature swings, mean temperature swings of much more than the couple of degrees we're talking about now of warming. It's had temperature extremes of 10, 15, 20 degrees C over relatively short periods of time, like centuries, during the violent swings of ice ages. And the Earth, of course, stayed habitable through all of that. So in the sense of true habitability for any form of life, it would take an awful lot to make the Earth uninhabitable. To make the Earth very difficult to inhabit for us without the aid of a lot of technology. I think anything more than 4 or 5 degrees of warming, or actually in the other direction of cooling, would make things very difficult for humans.
All right, the next question is from Somana, who's on with us live. Is it possible to destroy an asteroid coming to Earth, and how?
In principle, it's possible. We have nuclear weapons. They're not been all decommissioned. The U.S. has 7,000 or 8,000. Russia has a large number too. China has some. And these nuclear weapons, in principle, could be used to destroy incoming asteroids. That's actually a dangerous thing to do if you do it cavalierly or carelessly, because conservation of momentum says that if you literally made a head-on destruction of an asteroid, then the fragments you created will all keep traveling at almost the same speed in your direction, and you'd be hit by a set of large fragments rather than one huge thing. Not a good situation. So destroying an asteroid sounds nice, but it's actually not what you would want to do. The better strategy is actually deflecting the asteroid, because if you have sufficient warning of its approach and impact on the Earth, and that really just means a couple of years, you can send a space probe there, a massive probe, or a space probe with powerful rockets, and you can attach it to the asteroid, and you can essentially use the rockets themselves as a side thruster, like, of the asteroid. Now, the mass of the asteroid is huge, and the rocket power is modest, but if that rocket power is acting strongly and over a long enough period of time, you only need to lever the orbit or the trajectory of the asteroid by a very tiny amount before it goes from hitting the Earth to sailing by the Earth. And the techniques and the technology to do that, they essentially exist today. And that's one of the plans we have in our hip pocket if an asteroid were about to hit the Earth.
The next question is from Malik, who's on with us live. Are galaxies still forming?
Yes, galaxies are still forming. The universe is generally old and mature, and most of the galaxies that are ever going to form have already formed. So a large part of the gas and the dust that was thinly spread through intergalactic space has formed galaxies long ago. But there are still regions where galaxies haven't formed and where they could form in the future. There are also galaxies being destroyed or pulled apart by interactions and sort of unraveled, if you like, by gravity. And those pieces of galaxies may subsequently come back together to form probably a smaller galaxy. So galaxy formation is happening in a very small way, but the level of galaxy formation, that is the number of galaxies in a given volume of space, is lower by a factor of hundreds, several hundred, than it was at the peak of the galaxy formation era. So this is a very quiet time for the formation of galaxies.
Excellent. Thank you very much. The next question is from Pashupati, who sent an email asking, what are the main similarities and differences between Proxima Centauri's A, B, and C?
Proxima Centauri, the nearest star system, a distance of about 4 light years, is a 3-component star system. One is very close to a sun-like star. One is, I think, a little less massive than the sun, and then the other is a dwarf star. So it's a 3-star system, and 2 of the components, the ones that are closest to the sun-like in properties, could definitely have planets around them. And there's evidence that's still somewhat controversial, not fully confirmed, that there's at least one Earth-like planet around one star in the Proxima system. In the end, with good enough techniques, we could expect or anticipate there might be Earth-like planets around all 3 members of the system, because we've now started to find Earth-like planets around red dwarfs. So low-mass stars are just as good for looking for planets as stars like our sun. So essentially, it gives us a triple shot of looking for Earth-like planets in the nearest star system, which is very exciting.
The next question is from Deep Patel, who would like to know, how do rogue planets form despite not having a parent system?
The best guess, we don't know for sure, this is all based on simulations, is that rogue planets are ejected from their systems very early on, or right around the formation phase or slightly after. So planets form fairly quickly from a nebula where the central region collapses to form a star, and the debris left over tends to form a disk, and out of that disk coalescence occurs, and accretion, and the formation of planets. The early phases of planet formation lead to very unstable situations. The orbits are often chaotic. The planets can form quite close to each other. Some of them can have tilted orbits and interactions that way. And all of these things lead to a substantial probability that two of the objects in the early formed planetary system will interact violently enough that one is ejected from the system, or possibly both in an interaction. And so people have tried to put numbers on this by running simulations of planetary systems forming. And out of these early chaotic phases where the protoplanets or planets just formed are interacting with each other, and their orbits have not circularized, for example, and their orbits might be tilted, you quite often eject rogue planets, as they're called, and they will, of course, not have a parent star. In some of these simulations, you form as many rogue planets as you do planets that end up in stable orbits. That's a little controversial, so I don't know if there are as many rogue planets as normal planets, but there certainly could be a significant fraction of the number of regular planets as rogue planets, and there's no way to find them at the moment, because without the parent star, there's no telltale for their existence.
The next question is from Russatone, who's on with us live. And the question is, do stellar and galactic distances mean that living civilizations, like civilizations throughout the universe, are living in perpetually different times? Then would that make it impossible for any one of these civilizations to ever communicate?
It's an interesting issue, the idea of communication, because it's all bounded by the speed of light. So if civilizations are rare in the galaxy or in any galaxy, then the average distance between them is going to be large. And that increases the probability that the time it would take for one signal to go backwards and forwards, or to have a single round-trip communication, might be longer than the lifetime of the civilization itself. And if you do the math of this, the boundary point is about 3,000 years for the lifetime of a civilization. If civilizations are rare enough that the distance between them is 3,000 light years, then likely you can't have real-time communication, because the civilization no longer exists when you receive your signal and send back a reply. And that's a real issue for the whole idea of communication among civilizations. They are essentially dealing with their own cosmic time.
The next question is from one of our live viewers. Is it possible for stars like Sirius to have planetary systems?
Sure, it's possible to form planets around any star, because star formation is an inefficient process. The bulk of the mass in most simulations of it and in the theory of it does go into the central star, 99%, say, typically. But what's left over is substantial enough to form plenty of planets. And so, yes, a star like Sirius could indeed have planets. They're less likely to be habitable planets given the luminosity of that star and its activity.
All right, the next question is from one of our live viewers, and Akanshka would like to know, sorry, I'm terrible with the pronunciations, my apologies, but what causes quantum entanglement?
Quantum entanglement, we don't think it happens naturally. It's a state of matter that can be arranged. We can create coherent situations where two atoms, two microscopic states, are linked and they share a state. And one way to do that is just to have them share information by radiation, by photons that travel between them. And typically the entangled state has to occur at a very low temperature. So that's typically how it's done in the lab. So quantum entanglement is a construct, it's a technology, it's a technological situation. But what it means is that two atoms that are not in direct physical contact, they're not right next to each other at the distance that normal atoms are in a solid substance, but they're at some large distance, and by construction, you can create a coherent state such that the one atom and the state of the other atom are coupled. And so if you change the state of one atom, this atom that's separated is changed too, and that's an entanglement.
All right, thank you very much. I think this is going to be the final question for today. We are about 10 minutes past, but we started a little late. So the last question is about the universe. Is there any limit to our universe? Can it stretch infinitely? Will it just keep growing? What is the future for the universe?
It's entirely possible that the universe we occupy is infinite because we don't see an edge. All we see an edge in is in time, not in space. There's a distance we can see out in space that relates to the time since the Big Bang, how far light can have traveled in the time since the Big Bang from distant regions. That isn't to say that regions more distant than that don't exist. And in a sense, the theory does not prohibit that. So it's entirely possible that we live in an infinite expanding space-time. And if it continues to expand, then that infinite just keeps going and the universe just gets more and more diffuse, and that's what the future of the universe holds. It'll be very hard to imagine an observation that show that our universe is not infinite, because everything else we've seen so far in cosmology shows that there's nothing special about our location in time or space. Thanks very much for your questions this week. They're very good. I think we already announced the next week's session. So thank you for your questions. Thank you for Matthew and Alexander facilitating, and we'll be with you next week.